Okay, so I assume that you are all specialists of zeolite, and so that you know more or less the technique that we have developed in our lab during the last 5 or 6 years. This technique concerns the adsorption of xenon used as a probe for determining some zeolite properties which cannot be determined using the conventional physical-chemical techniques. And xenon is detected by NMR since this technique is suitable for the determination of the electron perturbations in rapidly moving molecules. We have shown previously that the chemical shift of xenon located in any given system is always the sum of terms corresponding to the different perturbations to which it is subjected. So we see on the first slide that when xenon is adsorbed in a zeolite, the chemical shift is given by these 4 terms. The first one is a reference. It is generally the gas at very low pressure. The second is due to the interaction between the wall and the xenon. The third one is the electric field due to the cation. And the last one is the excess of shift due to the xenon-xenon collisions. This last term is proportional to the density of adsorbed xenon, and so for a given concentration per gram of solid, it is proportional to the reciprocal value of the free space. So on the next slide, we consider now a xenon adsorbed in phosphosite structure with different silicon over aluminum ratio from 1.3 to 55. And we see that if we plot the chemical shift against the number of adsorbed xenon, all the experiment forms are on the same straight line. This proves that at room temperature, when we have a sodium cation, the influence of the electric field is negligible. This is due to the fact that the residence time of xenon on the sodium cation is very short, because the interaction between cation and xenon is weak, and so the time average of this electric field is negligible. So we assume now that when we use a zeolite with the sodium cation or in the acidic form, the electric field will be negligible. We see on the first transparency the chemical shift of xenon adsorbed in different zeolites containing only one type of zone where xenon is adsorbed. That is, only one type of channel or only one type of cavity. And we detect in that case only one component, and we see that the chemical shift variation against the xenon concentration depends on the zeolite structure. The slope varies with the structure, but this is normal. We said that the excess of shift, I forgot to tell you that when the electric field is negligible, the chemical shift is only the sum of 2 terms. One at 0 concentration is due to the influence of the structure, and after the increase here is due to the xenon-xenon collisions. And the slope of this variation is proportional to the reciprocal value of the free space. And so it is normal to have a slope which depends on the structure. But we see also that the chemical shift at 0 concentration, NM delta S, depends on the structure. I remind you some characteristic of void spaces and the corresponding chemical shift at 0 concentration, NM delta X. And we see that the chemical shift for ZT4 is larger than for phosphosite, not only because the diameter supercage. But also and mainly because the diffusion of xenons through the alpha openings, whose diameter is about the same as the diameter of xenon, 4.4 angstrom, is smaller, is more difficult than the diffusion through the 8 angstrom openings. We see also that we may have the same, roughly the same chemical shift for different structures. So the relationship between the chemical shift and the structure is difficult to define because the chemical shift at zero concentration depends on the structure of the void space, on the dimension of the channel and cavities, and on the ease of diffusion of xenon inside this free space. Whatever the case, we have exactly the same type of result if we consider SAPO or ALPO or MAPO. That is, the results are exactly the same if we have really a zeolite or if we change the nature of the chemical nature of the surface. We have, for example, here the SAPO 37 in blue, and we see that we have exactly the same straight line and the same chemical shift at zero concentration that we have for the Y zeolite. We have another example with the ALPO 5, SAPO 5, and MAPO 5. They are all on the same straight line, proving that at room temperature, the chemical nature of the surface, if we have only weak interaction, that is, if we have either an acidic form or a sodium cation, they are all on the same straight line, proving that the chemical shift is mainly due to the structure. So we deduce from these results that the chemical shift characterizes the zone where xenon is adsorbed. And so if now we have a more complicated system, either because the structure itself contains different zones for xenon adsorption, for example, different type of channels or cavities, or because you have a mechanical mixture of solids, or because you have an interrupt of structure, you must detect as many components as you have different type of zones where xenon is located. For example, for the ferrite, we have two different channels. Xenon can be adsorbed either in this channel C parallel to the C axis or in this rather spherical cavity along the B axis, and we must detect two signals corresponding to the location of xenon in these two sides. This is the B channel and this is the C channel, and it's possible to determine, of course, for each level of xenon concentration the number of adsorbed atoms in each side. Another example concerns the raw zeolite. You remember that you have a sphere connected to 6 prisms, and so xenon can be located in the prism and in the sphere, and in that case too, we detect two signals corresponding to the location of xenon either in the sphere or in the prism, and in each case there is a direct relation between the size of the zone where xenon is located and the corresponding chemical shift. You can also apply the technique for determining the structural defect. This is the Y zeolite which has been dealuminated, and we have here for a given pressure 150 torr, 1,500 torr. We see that we have the main signal corresponding to xenon located in the very well formed supercages, and in addition we detect another one corresponding to the structural defect, that is to the secondary porosity due to the dealumination. example concerning the mordenite, the illumination, we have the main channel and additional signal corresponding to the structural defect. On the next slide, next one. This is a mechanical mixture of two zeolites, calcium A zeolite and sodium Y zeolite. We see that it's possible in that case too to determine exactly what are the concentration of the two different components which are together. But of course it's an experiment completely stupid because you have two very pure zeolites and you do a mixture. But you may have exactly the same thing if you have an integrous of structure. This is the example concerning the inclusion of mordenite inside the ferrite zeolite. And we see that we detect 1, 2, and 3 lines. In fact, we must detect 4, 2 for mordenite and 2 for ferrite, but we have here at the same position the line corresponding to xenon adsorbed in the main channel of the mordenite and in the B channel of ferrite. Whatever the case, it's possible to determine exactly what is the concentration of mordenite inside the ferrite structure and at a very short range, because if you try to detect the X-ray diffraction pattern, you don't detect any mordenite at all. So it is clear that the chemical shift of zero concentration depends on the structure, of the size, of the free space, and of the ease of diffusion. But all these previous results are only qualitative results. If we want to be able to use this technique for determining precisely the dimension of the zone where xenon is absorbed, if you want to determine exactly the free space of an unknown structure or the dimension of the defect after the illumination, for example, it is necessary to have a quantitative relationship between the chemical shift and the structure. And we have thought that the parameter able to define altogether these different things, that is the size, the structure, the ease of diffusion, is what we have called, what we have named the free space, the main free space imposed by the structure. We assume that xenon is absorbed at the surface with the corresponding chemical shift delta E, depending, as it has been shown by Eric, depending on the curvature of the surface, and it has the possibility to move, to diffuse inside the channel, so coming from this side to another side here, and after to another one. And it has been possible to determine the distance between two successive collisions, and after each collision to determine the average distance for all these previous collisions. And when this average distance is constant, it is the main free path imposed by the structure. It is exactly the equivalent of the main free path in the gas phase, except that here it is imposed by the structure. For example, this is the case of mordenite channel. In black, the point black corresponds, here we have a distance which is about 15 angstrom and which corresponds to the distance between the 20, maybe 32 and 33 collisions. Here is the distance between the 69 and 68 and 9 collisions. Of course, we have a random distribution of the distance between two successive collisions, but we see that little by little, with the increased number of collisions, the average distance of this successive L value become constant, and we arrive at an average value which is 2.45, and which is the main free path imposed by a structure. And so if you plot now the chemical shift against the main free path, which is of course directly connected with the structure, we have the blue line. And if you plot the reciprocal value of the chemical shift against the same value, you have this straight line. And now from this straight line, it's possible, knowing the chemical shift of xenon adsorbed in any structure, to determine the main free path and to determine the size of the zone where xenon is adsorbed. For example, it has been possible to give some information to the free space of the beta zeolite before any publication of the structure, and to show that the free space of the beta zeolite is as open as the free space of the phosphidite, and to give some information on the real dimension of this free space. So the last point concerns the temperature of the calibration. We have done the measurement at room temperature, and we have given the calibration between the chemical shift and structure at room temperature. And the question is now, is this temperature the best one for such calibration? The reply is, it isn't the best, but it isn't far from the best. If now you study the absorption of xenon, for example, in a phosphidite structure, at a different experiment temperature, we see that we have, of course, an increase of the chemical shift when we decrease the experiment temperature. The main reason being that xenon is staying now more and more on the strongest absorption side. The residence time of xenon on the surface is more and more longer, much longer, and so we see that we increase the chemical shift, and about 60 or 40 C degrees, minus 40 or 60 C degrees, we start to have such a curvature, which is characteristic of a stronger interaction between the cation and xenon atom. But we see that when we increase the experiment temperature, we arrive to a limit of the chemical shift, which is really the real chemical shift when the residence time of xenon on the surface is completely negligible. I repeat the model. We assume that the xenon is able to move everywhere, to collide, to strike the wall, and the chemical shift detected is given by the value of the chemical shift of adsorbed phase, and of course of xenon flying from one side to another one. Each one, of course, weighted by the probability of such step. Of course, delta V depends on the structure. If the distance between two collisions is long, delta V, we have enough time to lose the memory of the perturbation. On the contrary, if this distance is very short, the average value of delta V will be lower than delta E, but not far from this value. And this is the reason why, if now we do the same experiment with ZSM5, the variation of the chemical shift against the experiment temperature is very small. We have roughly the same chemical shift at 26 degrees and at 100 C degrees. So what is the best temperature for the calibration? This is the variation of the chemical shift at zero concentration against the experiment temperature. If we want to study mainly the structure of the zeolite, we have to work above about 20-25 C degrees. We see that whatever the chemical nature of the structure, we have, for example, sodium Y zeolite, we have here the illuminated Y zeolite. We see that at low temperature, we have a large difference, but above about 25-30 C degrees, all the results are on the same line, proving that at high temperature, the main influence is the structure. Of course, the difference is very large at high high and low temperature when we have very open structure. If on the contrary we have a very narrow channel, we see that whatever the experiment temperature, we keep roughly the same value. So if you want to use this technique for determining the dimension of the zone where xenon is absorbed, you must work at high temperature. If you want to determine the nature of the chemical species which are in the channel or in the cavities, you have to decrease the temperature, because we see, for example, here a large difference between the sodium white zeolite and dealuminated zeolite. The main reason is that in the dealuminated zeolite we have some aluminum extra framework in the channel, and in that case the main interaction at low concentration and low temperature is the interaction between the extra framework aluminum and the xenon. A few minutes? 5 minutes, just a minute. The last example concerns the example which has been chosen by Eric a few minutes ago. It is the ZSM 11 structure, Alpha 11 and Sapo 11 structure. It says that there is an elliptical section, and the distance of the small axis is roughly the same as the distance, as the diameter of xenon. In that case, when xenon is absorbed, we have a permanent perturbation along the x-axis. On the contrary, in the y-axis and in the z-axis perpendicular to this plane, the xenon is completely free. And so you must detect in this case an anisotropy of chemical shift due to this permanent perturbation in only one direction. And in that case, you detect such signal. On the contrary, if now you increase the xenon concentration, you increase only the xenon concentration in the z direction, and so you increase the perturbation in the z direction. And so now you have two permanent perturbation, one in the x direction and one perpendicular in the z direction. On the contrary, in the y direction, the electron cloud is completely free. And so you must change the anisotropy of the chemical shape. And it is exactly what happens. At low loading, at a low xenon concentration, we have such anisotropy of the chemical shape. At high concentration, we have changed the axis of symmetry for such chemical shift anisotropy. And of course, at the intermediate concentration, you haven't any anisotropy at all. So you can also use this technique for determining if you have the symmetry of the structure, of course, at a short range. Thank you very much.